Oh boy, we got 3 Alpha all the way up to part of 4 Charlie to do. At least that's where I'd like to be before we finish. So we got a minute or two. Anybody have any questions on the last segment that we did?
Can't think of any, sir.
Yeah, I see Elder is lit, but I can't hear him. Can anybody else hear him?
No, sir.
No, sir.
He is churnt right now.
I don't know. It was doing that for me last stream as well. I don't know if it's like an error on Discord's part or something.
It could be. Yeah, good afternoon, Terminator. Wow. All right, so I had a couple things that I wanted to show you. Well, actually one, but I wanted to address. I can't remember who asked the question of, does it increase speed for the hierarchy? The answer is yes, it does. It went online. When you start adding multiples of aggregates, it will speed up. So when you do an upload test and a download test, you should see something along the lines of either a T1, T2, T3. Back in the day when I had a 56K modem, I was very surprised to see I had close to a T1 line. Woohoo! Not anymore. That's a bygone era. So let me do this. Go ahead.
I was just thinking, since it's going through multiple multiplexers and devices, it would. I understand the bandwidth increasing.
Mm-hmm.
I just thought it would go slower since
Oh no.
that's more.
You're adding your multiplexers when you look at, the first one's 1.544. Okay.
Right.
The next one is 6. Well,
right.
Isn't that an increase in speed as well as bandwidth? Yeah. I went back and I looked and went, yeah, it is increasing on everything. So, but they don't want to go beyond the 4, but I did do a little bit of research and they seem to think that they may have a solution to it. So, which is, and we're talking wired, we're not talking wireless or fiber. So fiber actually puts a little bit more into it. But I didn't get into that. I just was looking at the regular wired portion.
Right. Well, for me, I was just trying to think about it as an example, an analogy. It would be say you're a bus and you go on a ferry, and I guess a ferry, you go on a bigger ferry or whatever, and then keeps on going bigger and bigger. There's more people being delivered to the same place. It's just that it's not as fast as if you just went on your own. No.
That would be true utilizing that scenario, yeah. But with multiplexers, your aggregate rate is your speed. And when you start adding multiplexers, your speed starts increasing. And that was the reason why I said when you get to a T4, you have something called superscripts, because it's going so fast, it generates errors, and you don't want that. Let me see which one this one is. I think it's... There we go. Here's the other thing that we were talking about, the cable lines. You can see the amount of connections that's going to Europe. And then, who is it that lives in Alaska?
Me, sir.
Okay.
Oh, I did.
There you go. Would that explain why? If you're living in the mid-state, you're going to have issues just trying to get it to where you're...
I'm sorry, sir. Where am I looking at?
You don't see it? Oh, wait a minute. Duh. Hang on. I'm sitting there trying to show you stuff, and I forgot to do this. That make a little bit more sense?
Yes. Oh, yeah, sir.
Now, they call this a submarine cable map. Okay, whoops. Wrong one to grab. But you can see Europe and how everything is lined up. I'm surprised it's on this side of Greenland. I thought it would have been on the other side, but there's Air Force bases up in here too. Thule, Greenland is a place we have. When you get to Alaska, you can see the amount of cabling that we have here. So, like I said,
what are those cables for?
those are underwater cables. In other words, in order for us to connect to Europe and to connect to, in our case, if you take a look at this, to Japan and Australia and all these others down here in the Asian part of the world, it's all a underwater cable. And again, this was pulled off of www.submarinecablemap.com.
So, like, if you're gaming in Europe with somebody in, like, the United States, would it be connected through those cables?
That is correct. That is correct. You know, and they're stations that they come up into. I wonder if I can make this. Nope. Oh, this is giving me. This is American Mobile Submarine Cable System 1. I don't know if you can see it, but you can see it looks like the upper part of Florida is where the station is, as well as probably Miami, and how they drop those cables to get to Guatemala and Honduras and Colombia. Wow. So you can see that this, I mean, I just pulled one up just to see what we can do here. Let me pull up another one. That's North America. But on the side here, you can see where you can select. Yeah, I can barely see it, but it gives you an idea of where you could. And it's just narrowing these cables down.
Yeah. I'm just glad I had fiber in Alaska, because I feel like if I didn't, that would have been painful.
Mm-hmm. See, I've played when I'm on my server. I'm linking up to right in here because I've got some people I play with that's in Germany, France, and Spain. And the ping rate goes, you know, in the stateside, I'm looking at a ping rate between 60, 70. When I get overseas, I'm looking at ping rates in the 200.
Yeah, 200.
So that's a lot of delay. It's a lot of delay when you're playing these games. All right, so let me get out of this and go to the, oh my gosh, we got to cover this. All right, so we're going to look at the identify basic facts about principles, capabilities, limitations of SATCOM or satellite transmit and receive systems. This is the basic facts, not, you know, breaking down one of the GSC 170 or the TSC Tango Sierra Charlie 179 that we looked at earlier as far as a handout, because the NSM is part of the SATCOM system that you're going to see in Block 9. Of course, all comes with the Air Force application. You're going to deal with SATCOM equipment, period. We're going to look at the basic radio picture, fundamental radio parameters, radio performance assessment, ancillary functions. And this is just going over your NSM 50, You can see where our NRZ is here, your CDI is here, your T1E1 are here, and your HISI ports are right here. So if you
sir.
had...
Your stream is
Yeah.
Oh no, that's not good.
Where, sir?
Let's try to go back to this again. I wonder if it was when I switched. Can you see that now?
Yes, sir.
All right. Thank you for
Right
reminding
there.
me. Sometimes Discord likes to bump me off. So I wonder if I was going between the windows, it bumped me off at that point. So did you see this objective?
No, sir.
Oh, you did not? Okay. So I apologize for that. I don't know why they did that. So anyway, objective, there you go. Basic radio, there's the AFSC application.
Wait, sir.
Yeah.
So this is 3. Did we skip 2B, or is 2B the lab?
Okay. 2B and 2 Bravo and 2 Charlie is the lab. One is
Okay.
the program, the NSM, and the other one is troubleshooting. And we don't really go through troubleshooting a whole lot because you guys are the ones that put in your own problems and you have to figure it out.
Yes, sir. Okay.
I'm
Thank
sure
you.
you guys had problems, didn't you, when you programmed?
Yeah, somewhat.
Yeah. And basically it was you clicked the box that wasn't supposed to. Or you clicked the box that did something different that you were supposed to.
The one problem we had, or I had, was that when we were doing the inputs for the multiplexer and the demultiplexer, it'd be the same bit rate, but the aggregate would be different. And when we try to apply the config, it wouldn't work. And I just had to clear it and put it in again, and then it would work for some.
Probably didn't press apply down at the bottom. Because you have
Maybe.
to apply config at the end. I normally tell everybody to apply config after each tab that you go through. That way you know that you've accomplished it. And at the end, when you got all your lights that are supposed to be green on the software program, if there is an alarm, clear the alarms. Wait about 30 seconds. If anything pops up, you know you programmed something wrong.
Yes, sir.
So just hint for the next time you get into Block 9. Okay, there's the Air Force application. You're going to deal with SATCOM equipment. We're going to go through the basic radio picture, fundamental radio parameters, radio performance assessment, ancillary functions. This is what we were talking about earlier. On the back of your NSM. This one is case D. I think the one that you guys are dealing with was case A. It goes Charlie, Bravo, Delta, I'll think I would say Charlie, Bravo, Alpha. Delta is the other side. So if you get in the Block 9 room, and there's 2 rooms, you'll notice that there's 2 sets of 3 cases. One is Alpha, Bravo, Charlie. The other one is Delta, Echo, and Foxtrot. So case D is actually the first case in the second set of the TSC 179. So we have the basic radio picture. If you hadn't got one of these, you're cutting out on my side. Okay. Probably because I'm too close. Sometimes Discord has an issue. Let me turn it down just a little bit. Any problems with the mic now?
No, sir.
All right. Sometimes Discord does that. We'll see what happens. Check, check, check. Did it cut out then?
No, sir.
Okay. All right, basic radio picture. This could be one of the handouts. I'm not one to, you could color this in, do whatever you want to, or put your inputs in it. But we have one coming up real soon, so I don't see the, if you want to do the work, great. As reference, you can. We'll see this in just probably after the transmit, just to give you an idea. Helps if I'm on the right one. Okay, this is the objective of your basic radio picture. It comes in 3 steps. 3 steps are modulation, up conversion, amplification. This is for transmit. The objective for transmit is transmitting baseband to the distant end. Remember you were discussing about baseband earlier this morning? Well, here you go. Baseband is the multiplexer aggregate coming into the tisser, okay, or any type of equipment that is going to transmit it to the distant end. So those 3 steps, modulation, up conversion, and amplification, are part of that objective. Let's take a look at each one of them. So the modulator is going to take the baseband, which is an aggregate mission bit stream. You're going to hear the mission traffic is another one. Aggregate rate. Those are all interchangeable for the baseband. So a modulator does what it's going to do. It's going to modulate. It's going to bring that baseband up to a intermediate frequency. You'll see the normal 70 to 700 megahertz. On transmit, I don't like this part because it's actually 7 gig when you're looking at the tisser, the Jerk 239. Go ahead.
Is it okay to, I know you use the word baseband terminology for this block, but baseband is the composite signal, is that correct?
Yes. That is the
Okay.
aggregate that we've put all these users into for one data stream that's coming out.
All right, thank you.
You're welcome. The up converter is going to take that IF, put it into RF. How's it going to do it? Well, we use something called an oscillator. Oscillator is using phase-lock loop to generate a signal, combines it with the IF, and brings it up to the usable RF. Then we have a power amp. Well, anytime you manipulate the signal, you normally amplify it. In this case, because we've manipulated the signal by boosting it up using a mixer, there you go, high-powered amp. And that's going to help us get the RF to the distant end. When we look at receive, it is like transmit, just in reverse. So the reverse of transmit baseband to the distant end is you're going to recover it now. It's done in 3 steps. The 3 steps are in backwards order of transmit. So you're going to have RF signal recovery, down conversion, and demodulation. So let's take a look at each one of them. Low noise amplifier. This is meant to bring that weak signal and amplify it to the point where it can be used. There is some items that go along with it, i.e. the eliminates the noise. You got the down converter. It's going to take that RF that you just amplified and it's going to down convert it to a usable IF frequency. It's going to use a local oscillator. Oscillator being what's going to mix with the signal and break it down into a signal where we can pull the baseband out, which is the next one, the demodulator. So now you have demodulations, IF to baseband. It does have an AGC circuit in there. Anybody know what the AGC circuit does?
The automatic gain control.
Yeah, but what does it do? I'm sorry to step on you there. What does it do there, Airman Elder?
I was saying it basically keeps the volume the same.
That is
Or
correct. Now, I'm not sure if they gave you the full gambit in Block 2 or Block 3, but AGC is a received term. I've never seen it used in the transmit side. Transmit side is always ALC, TGC,
Yes, sir.
APC, but I've never seen AGC used as a transmit term. So automatic gain control means for a varying RF input. In other words, if you're way out there, that's going to be pretty weak. If you're close, it's going to be stronger. So that varying input, that AGC is going to compensate and give us that constant output. In our case, it'll be baseband. So here's what should happen in that last fill in the sheet. You have your multiplexer, which is your baseband or aggregate signal, mission traffic, you name it. Comes into modulator, modulates it to an IF. Your up converter takes your IF to RF, and then it amplifies and then out the antenna. On the receive side of the house, which is recover the baseband, you receive the signal, it boosts it up with the LNA, takes out the noise. Your down converter breaks the RF down to an IF. The IF comes over to the demodulator and it breaks it down into baseband, and then it gets demuxed out. Along with that picture, this is an easier way of looking at where the oscillators are in the up converter and the down converter. Without these, you can't up convert or down convert your signal. So the oscillators play a significant role in our basic radio picture. And if you hadn't noticed, it also plays a significant role in any radio that we have out there. Radio, SATCOM, wideband telemetry. Without it, you just don't work with it. So the next part of this is the branch assembly. The one thing about the branch assembly that we can say, it is all passive items, all passive electronic items. And you can see that we have different symbols in each one of these. Anything that you see with the arrows, an isolator. I think this is a directional coupler. This is a filter. This is a circulator. And again, another filter down here. Again, this is a passive system. And I'll show you this when we get into the C's and D's. What does the branch assembly do? You can read it. Big things are suppressing harmonics, selectivity. It does monitor the output power. And it does have some AGC selection in there where we pull the signal off in the receive side of the house. We're going to look at each one of them. First one is an isolator. Where the arrow is pointing is where the signal's going. Anything else that's trying to get back in, it prevents it from getting back in. This is a one-way item. It does provide some impedance matching. We have a directional coupler. This one is where we're taking samples. We're looking at the forward power, the reflected power, anything else that we need to do to see what our output power is going to do.
Why is it referred to as a dual coupler?
A dual coupler?
Directional coupler.
Yeah, forward power is going out to the antenna.
And then we have the reflective coming back.
Yes, that's the reason why they call it a dual.
Thank you.
Yeah, the last thing you want is reflected energy. I think your PRIC 113, I think when it reaches a 3-to-1, it goes from 10 watts to 2 watts. And that's that directional coupler doing what it's supposed to do by monitoring the output power, but it's also looking at the reflected power. Because the last thing you want to do is be in a wartime situation, your antenna gets blown off, but you still have 2 watts to be able to transmit out. You might not have 10, but at least you got 2. Next up, we got filters. There's a couple different kinds out there. Bandpass, notch. The whole idea is we want to pass certain frequencies when we're using a filter. So you can look at noise as being a problem, so that's where a filter would come into play. Circulators. Now circulators, you can look at YouTube, not YouTube, but Google it, and I think it's your duplexers are the strangest ones. Diplexers are one cable both ways. Duplexers actually it's a three-way tie point, and they use, I think it's ferrite, iron cores to differentiate between a transmit signal and a receive signal. Don't ask me how they do it, but I've looked at the background on those, and it's quite fascinating. I just can't put my finger on how they're able to do it using just those ferrite cores. Just some gee whiz stuff that you can look at. So we look at AGC. Now, we've gone over that a couple times. AGC is meant for varying RF input, gives you a constant output. What does it mean by varying? Well, the easy way to describe this is in the air traffic control environment. You got a plane that's 200 miles out, and they're making communications at the base. Well, that's a pretty far signal to be transmitting, so you're going to have to boost up your RF internally to get that constant output. As the plane gets closer, the signal becomes stronger, so the AGC is going to start breaking it down. If you didn't have AGC when the plane was 200 miles out, you're going to have to turn that volume completely up just to hear it. As the plane gets closer, you're going to have to constantly keep that volume turned down as they get closer. Now, what AGC does is it takes the human error out. As it gets closer, the circuitry allows that constant output. With RAGO, we're looking at the SATCOM version or the wideband version of that scenario. Because if you set the dish up and you're 2 miles away, it's going to be different than setting up the dish versus 20 miles away. So your AGC is going to be inconsistent from the distances that you're going to be transmitting and receiving at. So
what you're saying is RAGO is basically
it's an acronym.
You're saying it's basically the AGC but for SATCOM?
SATCOM and wideband and telemetry in this particular case. RAGO is how we use it in the TISR, the Jerk 239, which is a piece of wideband equipment. I've seen it used in SATCOM, the acronym. It just depends on it just depends on the manufacturer and how they set these things up to where you kind of understand it. Now, RSL means receive signal level. You're going to see this on the TISR on both the baseband assembly and the RF assembly on a meter. It's telling you how strong that signal is coming into your TISR. AGC is done in voltage, so it's a representation of RSL. Gain is what I want to do to the internal components to keep that output constant. So if you look at the boxes, if our RSL has increased, so will our AGC voltage. The idea behind it is if you got a receive signal that's strong, you got to bring the gain down to get the constant output. And it's vice versa when the signal is weak. So you could say that the RSL in that first box is let's say 2 antennas that are very close together, 2 miles, versus a 20-mile set of antennas on that second box. The idea is we need to provide some correlation between the two. RSL and AGC are directly proportional, like I just explained. And RSL and gain are inversely proportional. And again, the whole thing or the whole concept behind AGC is to keep our output constant. With aggregates or baseband or whatever you want to call it, you got to have a signal that is constant in its digital form. If it isn't, you're going to have problems when it comes to multiplexing and demultiplexing when it comes to this piece of equipment. Now we're going to go through some terms quickly. You have frequency, accuracy, stability, bandwidth, frequency response, selectivity, gain, and sensitivity. So let's take a look at them. You got frequency, accuracy. This is all dependent upon your oscillator. I've seen oscillators where they drift all over the place, and then I've seen oscillators where they do not move at all. They are dead on their frequency, and their accuracy is beyond anything I've seen. Most of your accurate oscillators are normally in the higher end pieces of equipment, like the HF gear with the single sideband. As far as SATCOM, I've not dealt with that as much, but there's older radios that I've seen that just their oscillators drift all over the place, and it's really hard to keep them on frequency. Technology has helped us with software-defined radios now. Okay, next up is bandwidth. You can see that it's between two different frequencies, the upper frequency and the lower frequency. That's what they're describing here. Frequency response, this is the range of which an audio device will either produce or reproduce a signal within a certain tolerance. Now, for those of you that have any audio gear and like to look at that stuff, look in the back of your manual and it will have frequency response. For example, the one I can pull off the top of my head, it's most stereo systems that are adequate are, their frequency response will say 20 hertz to 20 kHz, has a plus or minus 0.001%. I just can't even think of the darn name. Reproduction rate or whatever it's called nowadays. Next up is selectivity. This is how well that your equipment can process the right frequency and reject the others. You have gain and sensitivity. Gain is like your volume control on your radio. You increase the volume when you like the song and decrease the volume when you don't like the song, or better yet, turn it off. You have sensitivity, how well these radio can receive that signal and be able to pull the actual intelligence better than the noise. Now, I'm thinking that you guys did signal plus noise to noise ratio with the PRIC 113. Am I correct?
Yes, sir.
Okay, so there you go. It's determining how well your sensitivity is when you do that performance. Next up is your systems approach. What does this mean? It means that you can't just say, oh, my equipment's working good. You got to find somebody else. It doesn't work that way. When you're out in the field, you may have to do someone else's job just to make sure that, okay, my equipment's working fine. I need to call that person when they're available. Or you might have to fix their equipment. I've seen that happen way too many times out in the field. For example, if you've got your equipment tied to phone lines and you find out that your equipment's working just fine, but the phone lines are an issue, sometimes you have to get the phone people to help you out. And this is where you've heard the old adage, you can attract bees with sugar water versus vinegar. So take it upon yourself to be a little bit along that proactive. I'm going to look at your equipment just to make sure that mine is working just properly. So it will happen out in the field. Next up, performance measures. quality, reliability, and speed. We have quality, which how closely the output resembles the input. You got reliability, how long that system is available. In other words, it's not going down on you all the time. And speed, how fast it can process or how quickly you can set that equipment up, like the CTM15, right? Everybody's going, I don't like the CTM15.
I actually liked it.
Well, guess what? Would you believe that some of those CTM15 masts are actually part of the Jerk 239 system? Why? We can put the RF assembly on top of that mast, and it's 20 pounds to lift. And yeah, it doesn't come with your 3 sets of guy ropes. It comes with an extra set for 4, and it's done completely different than what you would think of with the CTM. It's in the CTM manual if you want to look it up. Excuse me, not CTM, the Jerk 239 tech order. Next up, we have switching, auxiliary, channel, performance monitors, and fault indicators. Switching, how quickly you can get between one equipment to the other. Normally, an automatic switch works well. The idea behind it is so you or the customer does not see the downtime that happens. Auxiliary channel, this is what the Jerk 239/Tisser is going to have. We have our own channel, and it doesn't degradate the mission traffic. What does that mean? It's like having your own telephone line versus everybody else. So in other words, while everybody is trying to get out, you're the only one that can get out because you have that line solely for your purpose. And you're going to see it's called order wire on the Jerk 239. Performance monitors as well as fault indicators. If the light is green, everything is working well. Isn't that a performance monitor? Sure it is. If you have a red light, more than likely you got a problem. So that's another fault indicator and a performance monitor. On the Jerk 239, you have a meter on both the RF assembly and the baseband assembly. Use it wisely because it's going to tell you what's going on with your wideband piece of equipment. You may hear a tone, which could be an indication you've got a problem. Not like a fire alarm or anything like that, but you may have some issues when you plug in the handset or headset and all of a sudden you have this squeal coming over it. So I'll let you know ahead of time that's normally because you plugged the headset in and it hasn't quite met up with all 3 segments of the phono cord or phono plug. It does it. So whatever you do, don't put your headset on when you're listening to the 2.6 kHz tone because it will blast you out. There is no volume control for it. So when you're doing your checks, don't put the headset on. So there you have it. Basic radio picture, radio fundamental radio parameters, radio performance assessment, and auxiliary functions. Questions? I know we went through it fast, so. Questions?
Good.
Anybody
Trying to
else?
see what I don't understand.
Okay.
I think I understand most of it.
Okay. Well, I'm going to put this out there for you guys. I am normally on Discord a lot, to include the weekends. Yes, I play games, and I'm normally with my platoon mates when we're playing tanks. So if you throw me a message, I'll probably see it. And I will try my best to help you out in a timely manner. So just putting it out there. So if you got some questions, you're doing it over the weekend, and you got something that you just baffled by, do a message. Send me a message. All right, so the next one is
Appreciate.
not a problem. I try to make myself accessible because I'm at home. I just, I enjoy this stuff, just trying to help you guys out and doing the streaming. So whatever you want to do, I'll try to help you with it, and we'll go from there. Yeah, I remember my World of Tank days. Yeah, I played World of Warships every now and then with my brother. He's the one that got me interested in it. Yeah, that's true. You do get people on there that rage. You need to go to Block 4 on RF transmissions and look up mutual interference. And you'll get a laugh out of it. Don't laugh when I drowned, okay? All right, so next up we have identify basic facts about principles, capabilities, and limitations of modems. The RF transmission system technician, you will see that we've got modems tied to our devices. We're going to look at general modem principles, types of modulation, forward error correction, interleaving, traditional modems, and IP-based modems. What does a modem do? Well, it's going to modulate the carrier into a digital signal and send it to the distant end. I don't like saying that, but it is an analog carrier with digital intelligence on it, like your PRIC 150. And then when it comes in, you're going to demodulate it into that digital signal. And everybody's going, what do you mean it's an analog carrier? I thought it was all digital. Well, remember our signaling formats don't go very far, especially if they're 5-volt difference of potential. Well, by modulating them on a analog carrier, remember AC goes farther than DC will ever think about going. And if you didn't watch the History Channel's information on, what was it, Tesla and Edison, that's quite funny, to say the least. They did a good job on it. So baud or baud rate, baud is the speed of the bandwidth. Now you're going to hear something a little bit unique, which is called symbol rate. This is how we're going to figure out to get baud rate, or what's called symbol rate. And symbols can be all the way up as many as 10. I'm sure that they are working on more. So let's dive into it. You got a modulating type.
So were you saying that baud and symbol are one and the same?
That is correct. I don't know why they call it symbols or universal to baud. I've not read up on it, so I don't have an answer for you on that one.
I have a question, sir.
Sure.
So in the modems in your house, do they have their own multiplexers in them, to multiplex all the devices on the network going out when it transmits to the either through Ethernet or however it goes through the internet? Does it modulate? If your modem in your house, does it multiplex all the data coming from the devices or from the router?
Yes, it does. It's a simplistic form of multiplexing, but they don't classify it as a multiplexer. They're more interested in getting that aggregate onto the carrier signal. That's what modems do. Then you have a router. So it's just the combination of the two. You could, for example, up in my attic, I have a 16-channel switch as well as a 8-channel hub, and it goes all into my modem / router. So you could say I've got multiple devices, and they have to be multiplex. There's no other way around it. So when it gets put on that carrier, it's, in all reasonable senses, you could say it is multiplexed into an aggregate signal, modulated, and then sent out to wherever it needs to go. So yes, very good observation. Okay, we have three different types that we look at: frequency, amplitude, and phase for our modulation. Frequency is shifting the frequency, and everybody has heard of the SOS that the Titanic did. They call that Diddy Bop. This is your ones and zeros. You got a dash or a dot. Get it? Diddy Bop. That's what they call it. This is a 1 bit per symbol. You're going to have ones and zeros. This is what it looks like as far as a waveform is concerned. You have zeros are one frequency, and then ones are a different frequency. See, ones have a higher frequency and the zeros are a lower frequency. Next up, we have amplitude shift keying. Again, this one's going to, instead of varying the frequency, this is going to be varying the amplitude for the ones and zeros. So far, 1 bit per symbol. Here's what it looks like. You can see our ones are a higher volume and our zeros are a lower volume. Next up, we have phase shift keying. Yeah, there's a couple different types in here: binary and quadrature. Binary is the first one we're going to look at. This one is going to shift our AC signal a certain way for ones and zeros. It's also 1 bit per symbol, and as you can see with this, anytime that we have a continuance of signals, nothing is going to happen, so you can't really verify that there's 1 0 or 2 zeros in this case. And that's where the clocks start coming into play. Okay, you have a 1. You can see that we've used our signal, and when we change from the 1 to the 0, it always changes. It appears to change in the top part of the signal and reverses itself. A 0 is going to shift on the lower part of the signal, and so forth and so on. So as you can see, we're shifting the 180-degree mark. Quadrature, if you take a look at this, this is one complete waveform for each of these particular pieces of data. Now when you get the quadrature, it's a little bit different. Quadrature means that you're going to shift it not only at the 0 line, but you could also shift it at either the crest or the low end of that AC signal. So in other words, there's 4 places it could shift versus 2 places it could shift for BPSK. Now with QAM, that becomes a whole new entity. But quadrature is the start of where, instead of it being 1 bit per symbol, it's 2 bits or more. For quadrature, they've seen everything from 3 to 10 bits. So let me try to put this in perspective with you. Okay, so you had analog TV. They transmitted out anywhere between, I think it was 280 all the way up to 520 as far as lines of resolution. Well, when they went to digital, they increased it from the low end to the high end, from I think it's 480 now to 720 to 1080. So you can see how QAM in this case is helping us out. Now they're getting to the 4K. I've seen the Japanese coming out with a 10K. So right now our internet can only handle the 1080. The 4K is coming soon. When, I don't know. We'll figure it out. But like I said before, the Japanese have come out with a 10K. So all this has everything to do with the type of modulation that you've got to dwell with. So let's take a look at forward error correction. So we switched from modulation types to forward error correction. Now, what is forward error correction? Well, the big thing is I don't want to keep retransmitting the same line of information over and over and over again. What does it mean? It means that if I'm on the distant end, I got to have a pretty expensive piece of equipment to store all that data and put it together when I get many different pieces of it to make one picture. So it doesn't make any sense. So when they came out with forward error correction, they started on the transmit end, and they would transmit X amount of bits, and they would send what's called an error code to tell the distant end how to put it together. Because with noisy lines, forward error correction helps a lot. So when we look at forward error correction rates, we look at the half, the 3/4, the 2/3, the 5/6, the 7/8. What does that mean? Well, if we look at the last one, the 7/8, it means that I sent 8 bits of information. 7 of those bits were the intelligence. The 8th bit is the correction bit. The idea behind this is so I don't have to keep resending the data, and the distant end can actually put it together. It's kind of like Wheel of Fortune, you know, when they do the last wheel where they give you, you know, all of some vowels and a couple of letters, and then you got to figure out how to put all that together so you can solve the mystery or the puzzle. Well, that's what it is. Now, under forward error correction, if you were to take a look at this on YouTube, it falls under the words Hamming, Hamming code. What that Hamming code does is it shows you how it puts the forward error correction back together, and it's all mathematical. So again, forward error correction rates with this half, 3/4, you know, I'm going to go through it again. The half means I've sent 2 bits of information. The first one is the original bit. The second one is the error correction code. 3/4, that's 4 bits. 3 of the bits are information. The 4th one is the error code. Same with 2/3, 5/6. Does everybody get that? I've had some people just go, what? Everybody good with that one?
Yes, sir.
All right.
Yes, sir.
Okay, so what does this have to do with anything? Well, in order for us to figure out our baud rate or symbol rate, first we got to figure out what the data rate coming into everything is going to be. Then we got to figure out what the modulation type is as far as bits per symbol. And then we also have to look at our forward error correction factor. So all this plays into this box, which you could classify as a modem in this case. You got the data rate coming in, you got the forward error correction, putting it all together, then you're going to modulate it, and depending on your symbol rate will be your baud rate / symbol rate in this case. And I say symbol rate, I was referring to the modulation types. So when you put all 3 of those together, there is a mathematical equation to do it. I'm not sure if it's in your study guide workbook, but it gives you an idea how everything is put together to figure out what it is at the end. I'll wait till Airman Krause gets done. Gives me a chance to drink some water. Oh, okay. Well, that would make sense. Now I'm taking, you had to look at the ECM for that too, right? Okay, see, I've played with those things. I wonder if you knew how to figure out what your points were on those things too. When it comes to your distributor, having to line those things up. Whoa. Older cars were funner to work on, but man, they got temperamental at times. All right. So, going on to interleaving, Aaron Krause is going to town. Quickest key is, yeah. Yeah, I had to get rid of all mine. Mine kind of rusted out when I got down here. I had an old 78 Ford. I miss it bad. All right, interleaving. This is not to be confused. It's interweaving, whatever you want to call it. But interleaving, this is a form of forward error correction. The big thing is I'm sending the forward error correction, but I'm weaving, you're weaving information in there, but it's called interleaving. This is the forward error correction. The idea is you're only losing a piece of it instead of the whole block. And this comes with transmitting packets. Because sometimes when you're transmitting packets, you're transmitting the whole data stream at one whack. Next up, we look at traditional modem types. You got a telephone modem, a SATCOM modem. The difference is the telephone modem is old. SATCOM modem. I'm not sure if you got to see the iDirect modem off on the left-hand side of room 116. In other words, you had your 3 cases on the right-hand side, and then there was this rack of cards that you could see, and that was your iDirect modem. That was it's attributed to going to block 9's 118 and 120 rooms, and when they fire that thing up, it gets pretty loud. Anyway, that's your SATCOM modem, the iDirect modem. In fiber optic modems, however, because of their style, they operate in 5 stages. The nice thing about I love fiber optics because they say not susceptible to RF or electromagnetic interference. That's because you can visibly see it. They're higher than where the electromagnetic interference is, so they don't get interfered with. So you're dealing with a modulator, a transmitter, a receiver, filter, and demodulator. That's how it works. So if I'm transmitting the signal out, we always try to start with transmit. You're going to go into that modulator, transmit it to the distant end. The distant end is going to receive it, filter it, and demod it, and then send it where it needs to go. Your IP modems, you're dealing with this through your Wi-Fi. It's always on. Also, when, for example, mine is wired, I don't necessarily have to hit the Wi-Fi, but it's always on. When I fire up my computer, I can access my internet real quick. And here's where the iDirect modem came into play. Multiplexes. You got 30 terminals onto 4 carriers. The 4 carriers are what we look at. FDMA, that's frequency division multiplexing access. Just comparing between TDMA and FDMA. Now, here's where the iDirect gets its CX, KU, and KA bands. This is approximately 2.3 to 40 gigahertz. Now, the C band is the lowest, the KA band is the highest. There is a band that is missing, not the K-pop band either, for those of you who know what I'm talking about. It's K-band. Yeah, well, I figured somebody would figure it out. The K-band is in between the KU, which is KU meaning under the K-band, and KA meaning above the K-band. So if you were to type in those 4 in Google, you would find a frequency for each one of those bands to include the K-band. I don't know why they did not include the K-band. It could be just the way the iDirect modem is set up, or authorization is the big thing. So these are modems that you could have when you have multiple multiplexers out there that go into one of those 4 bands. So we've looked at general modem principles, types of modulation, forward error correction, interleaving, traditional modems, and IP-based modems. Any questions so far? I know I've gone through them pretty quick. Now's the time to ask.
I'm a little confused on the baud versus just normal bits per second.
Okay, bits or bytes. Okay, bits is basically the word, right? Here, let me pull up. Let me break this down here. I don't want to steer you in the wrong direction. Bits and bytes. I've been known to confuse the best. Okay, 8 bits for every 1 byte. Okay, 8-bit is a word. 1 byte is 8 bits. So you can take a look in this little area, megabit, megabyte, often the way to express data rates. So there is a way to figure this out the way they've got it. So the small b is a megabit. The big B is bytes, which is what we're dealing with. So we're dealing with words. Does that kind of clear things up for megabits versus megabytes?
Yes, sir.
Okay. Now, the other part of that story is when we're dealing with, let me get back up in here. When we're dealing with the symbol rate, we're dealing with the data rate. You can see that's the small b, so that's bits. What are we dealing with out here on the symbol rate or baud rate? Is that what you're asking?
Yes.
So
I think so.
Okay, so let's go in, and Google is wonderful. Can't spell either. It's called the old fart. Well, come on, guys. What? Oh, good grief. I brought Audacity up. Really? Fat fingered something. Oh, symbol rate right there. Wow. Symbol rate, also known as baud rate and modulation rate. Okay. It's a common measure of symbol rate. Symbols per second or pulses per second. Okay, so it's bits per second. How fast versus how much data you're transmitting. Wow, I didn't know that.
So are there like different types of baud just depending on what operation you're using?
I'm a little confused about that question. Help me out here. See if you can't reword that.
From what I understand, like a baud rate is like how many times a signal could change. So,
Which would be a bit.
right. So, but isn't it possible that a signal can change more than 2 times?
Well, it's either going to be a 1 or a 0. So how that is taken into context depends on what I would classify. Remember when we went and said that we had 2 bits per symbol?
Right. Well,
Okay.
I was thinking, like if I'm sorry.
Okay. For 1 bit per symbol, it's either a 1 or a 0. For 2 bits a signal, you're looking at 0 0, 0 1, 1 0, or 1 1. Notice that there's 2 bits in there, and each one of those bits has 2 different states that it can be in, but it actually has 4 different scenarios with that.
So at that point, that baud would be equal to 2 bits.
Mm-hmm.
Okay. So yeah. So technically, couldn't a baud be a different amount of bit size depending on like what operation you're doing?
I'm not going to confirm nor deny, but that makes it reasonable the way you put it. Yes.
Okay.
And I would have to do more research on it. In fact, let me write that down. You got my inquisitive mind going here. And that would be a quadrature, which is 2 bits.
Because I'm also thinking, like, if baud is like the speed of the bandwidth, why don't ISPs advertise in baud as opposed to bits per second?
Yeah. Well, I do know that the way they, because there is a difference between the small b and the big B, and I recently came across it about 2 months ago where, 1 is this much versus this one is this much as far as information was concerned. But let me hold back on you. We really don't need to know that. This would be an inquisitive thing, so I'll try to come up with some information for you.
Yes, sir.
Okay? I don't want to get off topic here and drown everybody out. All right, so are there any other questions before we go on? See,
I'm afraid they're not as inquisitive as us, sir.
I know, but hey, each his own. I encourage you to be inquisitive because that means you're actually listening and paying attention to what I'm going through. The idea is to get you to be interested in it. And I know some of this is just downright boring, but if it wasn't for my interest in taking a look at this, I can't add to it to where it becomes interesting. So your question on that's going to be an interesting one to research. I just hope I don't spend forever on it.
I have to represent for all the non-A1Cs in my class.
You just had to put that out there, huh?
Yes, sir.
Okay, let's look at 4 alpha. I'm still live streaming. Good. Identify basic facts about principles, capabilities, limitations of line-of-sight radio systems. Now we're going to go back to block 4 stuff. You remember block 4. We're going to have line-of-sight equipment, which is a TISR. We're going to be looking at these principles as well as repeaters and limitations of repeaters. Now, before I go any further, you have the electronic version of the C's and D's. On the very first page is our line-of-sight principles, and I'll show you this here in just a minute. The picture that I'm going to bring up here after this particular definition is in that C's and D's. So line-of-sight principles, what does it mean? It means that if I can optically see the antenna from point A to point B, I should be able to talk to it and make communication, so to speak. And that's both receive and transmit. This particular picture is in your C's and D's. What's missing is this part right here from our picture that we're showing you. If you look at your C's and D's, you will find that underneath this picture, underneath the true Earth radius, you will see the words 15% and 33%. It will show you. You will have this when you take your test. So C's and D's do come with the test or is available for you both in electronic and digital in the testing lab. So what does it say? It says radio horizon extends 15% farther than optical. In other words, optical, and you can see the optical hits right here. So radio horizon is this one. It's further out. And why is that? Well, it's because of the electrically coupled scenario. When you're shooting your line of sight out there, you're going to have some surface waves that is going to go farther than that optical. And when you compare it to true horizon is right here. That's where I can't see beyond the curvature of the Earth. So when you look at radio horizon versus true horizon, that's 33%, and then when you compare optical to radio horizon, that's 15%. So that just gives you an idea how surface waves are going to help us go out further. For example, if you've ever gone out White Avenue Gate and you saw what appears to be trees way the heck out there, that's actually Cat Island. And as you get closer down to where 90 is, they start to go away, but there is just that little top of the tree. That's your optical horizon. With radio horizon, now that's about 14-15 miles out there. With your radio horizon, it's probably going to go between 20 to 30 miles far, in distance. So twice the amount, depending on the frequency and the output of your radio. So this is some typically line of sight measures. You can see that we got 20 to 50 miles. Frequency range is 3 to 50 gig, 1.1 to 5 watts. We have, why do we use line of sight radios? Well, if you're doing multiplexing and you're sending it through wired lines, you're probably going to have to dig. And the last thing you want to do is in the middle of a deployed area is dig, because you don't have any machinery. You're all doing it by hand with a shovel and a pick. By using the radios, prevents you from having to do that extra duty of digging. Also, if you're doing, for example, you've got 4 observation posts and you need to make a small little base out there by using your repeaters, you can go farther out there. Now you don't have to dig at all. So there are 2 functions that a repeater does. You have frequency translation and amplification. What does frequency translation mean? Well, if you're transmitting on one frequency, the last thing you want to do is re-amplify it and transmit it at the same frequency. There will be interference. So what you do with frequency translation is you convert it into a different frequency and then send it out. Now you guys should have seen, or at least went through some information on repeaters in Block 5. Yes? No? Maybe?
Yes.
Okay, so this is not new to you. We're just trying to put it in context. The amplification, because of it's being a weak signal by the time it gets to the repeater, you got to amplify it as well as convert the frequency. And again, this is all in your C's and D's for the next couple pictures. Just the RF repeater and the IF repeater. We don't have the baseband or the audio repeater. So there's 4 different types. You can see where we've got the repeater set up here to go farther. Normally the terrain is the biggest issue. For example, you need to get up and over a mountaintop and all you have is line of sight, and that is the easiest way to get it from point A to point B to point C. So the first repeater that we look at is an RF repeater. What does it do? Well, it translates from one frequency to another, and you can see where we're receiving it at 440 megahertz, but we're retransmitting it at 4660 megahertz. The amplification, you see that we have a receive signal that gets the LNA, low noise amplifier, and then when we finally get everything retranslated, we send it out with an HPA, or a high powered amplifier. So that is the basics of an RF repeater. Let's look at the IF repeater. The biggest difference is I'm breaking it down. Instead of just readjusting the frequency from 440 to 4660, I'm now breaking it down to 70 megahertz, which is the IF, and then I'm going to retransmit it or convert it and amplify it and send it out. Now, why does that make a difference? Well, you have less distortion because you're breaking it down into more of a original signal. Yeah, it's only 70 megahertz, which is the IF, but at least I'm breaking it down to clear up some of that noise. The other two, which is the baseband and the audio repeater, they break it down even farther. For the baseband, and I've done this with the Tisser, is you can break it down to the baseband repeater. It is that simple because you're tying the baseband assembly to the baseband assembly of another Tisser and then retransmitting it out. That makes it a lot easier because then you don't have to break it down into something called an audio repeater, which is basically getting it down to the original circuitry. Talk about really expensive. This one isn't as expensive because all you're dealing with is two pieces or two sets of Tissers. You got one here and two here, and then on the distant end another one. When I say two sets, normally we come in a transmit and receive set, or so you can transmit and receive from one point to another. I would probably say back in 2008 and 9, we would take all the Tissers out. We would set up a multiplexer and a phone at Foster's Manor, shoot the signal from that Tisser over to the Levital building, repeat it, baseband repeater, to Jones Hall. Jones Hall would take the multiplex signal or the baseband signal, send it to the TSC 179, which would send it up to the SAT SIM inside room 120, send it up to the SAT SIM, bring it back down into the other pieces of equipment, demultiplex it, and they would be able to pick up the phone and talk to each other. I wish we could do that now, but hey, that's a simplistic repeater for you. So we have some limitations. For example, your equipment is the distance. For example, if you have only two pieces of equipment to go from point A to point B, and in the max is less than 25 miles, that's as far as you're going. I need to go 50 miles. Well, you might want to look at getting a repeater, but it depends on the money. If you don't have the money, it's not going to work. Another one is equipment capabilities. For example, the Tissers, only their max range is like less than 25 miles with a 2-foot antenna. If you get what's called the P2Ps, they can go 120 miles. That's a lot of distance in there. And next up is terrain. Terrain is a big issue because if you're trying to get up and over a mountain and you don't have the pieces of equipment, yeah, you're going to have some issues. And lastly but not least, that needs of the communication network. Do you need to get it there, or do you have an alternative for that? Just remember, noise factors play into how many repeaters that we can have. For frequency, it's 8 links before noise just drowns out your aggregate signal, and then TDM is 15. So we've gone over line of sight, repeaters, and limitation of repeaters. It's pretty much rehashing what you've learned in Block 5. Questions?
I have a question on the different types of repeaters.
Sure.
I don't understand why the RF repeater has the most distortion. Because I would feel like since you're doing less with the signal, you would have the most, I don't know, accurate reproduction of it.
All right. Remember that signal noise to noise ratio that you had? Have you ever listened to that? How low that signal is? It's normally what, a neg 97.5 dB down from 0. That's a lot of noise on there. And if you're receiving it, that's a lot of noise. And all you're doing is when you bring it over to, when you amplify it, you're amplifying the noise along with the signal.
Okay.
So when you get into the mixer, all that noise is there. So when it gets to your HPA, it's going to re-amplify all that noise and send it out. That's the reason why the repeater is that RF repeater is going to have a lot more noise than the IF repeater. What happens here is when you break that signal down to the 70 megahertz, you're getting rid of most of that noise.
So it's getting refiltered on the other repeaters?
Yes.
Okay, I understand.
And the farther down you get, the baseband's going to have more filters on it, and then the audio is, hopefully you got a lot of that noise out.
All right, thank you, sir.
Sure. Okay, any other questions? All right, so let's go to the next one. We're in 4 Bravo. I think I'm probably going to have to stop after this one, which is fine by me, and I'm sure it's fine by you guys. All right, Tropo. You guys should have had this in Block 4 briefly. We just mentioned it. This one we get into it just a little bit more because you're dealing with the troposphere. With the troposphere, there are pieces of equipment that you might have to use that use the troposphere, and it's an issue because you're having to broadcast a lot of RF in order to get it to refract back down to Earth to a distant station. So we're going to look at tropospheric communications, antenna terms, tropo antennas. So let's take a look at the first one. What is it? They call it beyond line of sight. That's not entirely true. It's more over the horizon. They can't go thousands of miles like the HF can, but they can get over the horizon far enough to where it's adequate. When I say adequate is we're looking at anywhere between 150 to 600 miles. What does it use? It uses a tropo. The idea is I'm going to saturate the tropo to where it's going to reflect is not a good word here, refract back down to Earth, because the rest of it's going to keep on trucking out to outer space. Mainly because of the frequency that it uses. Normally it's around 50 megahertz is the start of it, where you might be able to use it, but it's in the gigahertz where it's actually used. So what you can see from this picture here, that we're going to get some refracted energy back down to Earth, but most of it is going to go out through the atmosphere. Typical Tropocom is you're dealing with between 300 to 50,000 watts. Start to see a problem here. Anywhere from 350 megahertz to 8 gigahertz. Now, the 595 miles, I said 600 earlier. It depends on what website you go to. When this was made, they put 595 in there. Most websites will say between 580 and 610. They just picked that number because it was fun, I guess. And that's fixed. When we're looking at a tactical situation, like those mouse ears that you saw at the front of our Tropo, or not the front of the Tropo, the line of sight, they're tactical, and they're dealing with around 300 watts versus if it's fixed, you could go all the way up to 50,000 watts. Well, with this Tropo being 150 miles and 300 watts, the problem that you have with this is if the enemy gets any sight or gets a RF signature from the backward lobes of those, you've become a target. And that's the reason why you really don't want to be using Tropo in a tactical situation unless you're far enough away from the front lines. We have something called scatter volume or common volume. This is the area where it gets refracted back down to Earth, and everything depends on your receiving antenna. We have 4 different things that's attributed to troposcatter. And when they say compensates for blurring, they're talking about interference or canceling out the signal, things like that. For example, polarization. You're going to see that when you get into the TISR lab. You're going to have one end set up their antenna for vertical polarization, and the other end you're going to see it up for horizontal. The reason is for that polarization difference is so you don't transmit and cancel each other out. If both of you were on the same frequency, one was vertical and the other horizontal, you would have some serious issues. You wouldn't be able to communicate. But since you're approximately 200 plus megahertz away, and that's where the frequency comes into play when you're transmitting, then you don't have this polarization issue or frequency issue anymore. Angle, if you're on different frequencies, your angles are going to be different so they don't interfere with each other, and the distance between the two. When you're out there setting up your TISR, you are extremely close to each other. What should be happening is we should be able to space you out about 1 to 2 miles, but that's not going to happen on this base. And that space is important because the farther you go out, the less chance you have of getting dead on the first time. Normally it takes a little bit of finagling in order for you to link up with each other. So those are the 4. When we get into the TISR on Monday, I'll be able to explain the polarization and frequency to you better. Here is the common volume or scatter volume. This little area right here where it gets refracted back down to Earth. You can see we have the angles going on here. It plays a very important part in how we receive it. We have antenna terms with everything. You've seen reciprocity before in block 4. We just go over it the way, again, just to give you an idea of where that reciprocity fits in with our Jerk 239. Directivity and gain. The higher the directivity, the higher the gain. Lower directivity, lower the gain. This has everything to do with when we looked at gain back in block 4. We have frequency, and you could have easily put 2 and 2 together when you talked about electrical length versus physical length. Also, when you look at electrical length at 3 megahertz, your wavelength should be around 100 meters. When you're at 30 megahertz, it's 10 meters. So the higher the frequency, the shorter the wavelength, which also equates to the smaller the antenna. So if you were to look at 300 megahertz, you're looking at 1 meter. Wow. That's not very big. That's what, a foot? Not a foot, but 3 feet. So larger frequencies or lower frequencies need bigger antenna. Not to be confused with the dish. The dish is a collection of RF. It's what is behind it that antenna is going to be collecting or radiating determines the frequency. Type of antennas, there are horns and parabolics. Most people have seen parabolics. Horn antennas, again, you might have to rehash block 4 to take a look at it. We even actually have pictures here for it. You got, basically it's a pretty directional antenna. Parabolics, you're going to be dealing with the parabolics when it comes to Jerk 239. You got the front feed and rear feed. Ours is a rear feed. You have 2 different types of those feed that are, what the most common is, which is center fed and offset. And then your rear feed is either called a Cassegrainian or a Cutler. I think ours is called a Cutler for the TSC, not TSC, but the Jerk 239. This is a front feed. You can see where the antenna would be in this little area right here. This is center fed. Offset, you'll see on the antenna pad where those SATCOM antennas are. They are offset from the center. Cassegrainian is different from the... Oh wow, they're actually showing an antenna in front of the Jones Hall there that's on the pad. So there is one with the Cassegrainian. You'll notice that this is a parabolic subreflector. Again, your antenna sits behind the feed horn. So what happens is your transmitted path goes out the feed horn, hits the parabolic subreflector, bounces back into the dish, and then out. This makes it very directive in nature. With the Cutler, there is a piece of 2 pieces of metal on the end that either reflected into the waveguide or out of the waveguide. So we've covered tropo, antenna terms, and tropospheric antennas. It is 2:30. Is there any questions over what we've gone over today?
I had a question. Davis told me to ask it. He's just wondering if you knew what a 2-meter band was.
Yeah.
You know that, Davis?
Excuse me. 2 meters. Normally, what HF is, or not HF?
He's just trolling me.
Oh, is he? Yeah, a 2 meter band. Come on.
Yeah, I've been a ham operator for a few years, so early on I was asking if 2 meter was a recognized military term, and apparently no, it's just more of a civilian thing in the ham world.
That is correct. I've looked at the ham radio side. In fact, I highly encourage people to take a look at ARRL and their handbooks for information on antennas or frequencies or anything to that nature. They are very good in explaining it. In fact, Block 4 utilizes and references the ARRL book. So, yes, I'm aware.
What is the ARRL book?
It's Amateur Radio Relay League. It was formed back in the day when radios started coming in prevalent, and they wanted to have a civilian side for communications. So if you want to get your license, you go through them to play on the radios. And there's some unique circumstances out there because they're a civilian band, and they are very close-knit and have done a lot of experimental antenna designs. In fact, that's where the AT-197 came from, was a discone antenna that they invented. So they're very much on the front lines of developing different styles of antennas. The latest one is a J antenna. Did I say that right? Which is just simply half-inch copper tubing in the form of a J, and you have to solder your center conductor to a certain place in it in order to be resonant as much as possible. Look it up on YouTube. Is the way I can say it.
And them ham guys are always up to something.
Yeah, they are. In fact, they've done a lot of we have peer review papers for the scientists in their developing of different antennas. So they're quite handy dandy, even though they're not scientists in that state. That's my knowledge of ham radio. Any other questions out there? All right, so here's what's going to happen. It takes a while for me to post the recorded sessions. So probably tomorrow you'll see both of them pop up. Mainly because it takes time to load it to YouTube, especially when they're really busy. And I'll provide you the link. Did everybody see the links for the Quizlets?
Yes, sir.
Yes, sir.
Again, I can't emphasize that enough. If you get a chance, develop it even more. And if you do, just let me know so I can forward it on to other people. Last chance. Any other questions? All right. Well, you guys have a wonderful weekend. Don't get in trouble at the BX because they're not letting you off base yet, are they?
No, sir.
Okay.
Except for Bejarano.
Well, that's because he's got a spouse off base.
Yes, sir.
Okay. So that's the reason why. Are you at the house listening to this?
Yes, sir.
Smart. All right. You know what I told you about Discord? I can be reached at any time. Just give me like an hour or so to answer. Sometimes I'll answer in a matter of seconds, so it just depends if I'm in the middle of a game or not. You guys have a wonderful weekend.